So let's look at a couple more example problems of factoring polynomials using structure. Or in other words, we're looking for a pattern in our polynomial, either when it's a perfect square and can be written using this formula, or it's a difference of squares, where you have some numbers squared and you're subtracting some other numbers squared. And these patterns show up often enough that it's worth looking for them when you're trying to factor. And since this example problem is dealing with subtraction, and there's only two terms, this looks like a difference of squares. So the question is, when we rewrite this, we have 49q to the fourth minus 4. Can each of these terms be rewritten as something squared? So 49q to the fourth. Well, if we took its square root, so the square root of 49 is 7, and the square root of q to the fourth is just q squared. We can rewrite this as 7q squared squared. Since if you were to remultiply this out, you would get 7 times 7, which is 49, and q squared times q squared, you would have 4 q's multiplied together. And likewise, this minus 4 here, 4 can be rewritten as 2 squared. So this does seem to match up with our pattern here, this difference of squares. We have some expression squared, and we're subtracting some other expression squared. So we can match it up to the formula, since remember, to write this as our difference of squares in factored form, it's the first number, or first expression, 7q squared, minus the second one, ignoring the squares now. And then it's the first one plus the second one, again ignoring those squares. So this is what we think is our answer, but to check this, we'll need to redistribute and multiply it out. So the 7q squared will go to both. So we're just checking our work now to make sure this is the correct factorization. And 7q squared times 7q squared, that is 49q to the fourth. Then 7q squared times 2, that's plus 14q squared. And then we have minus 2 times 7q squared, which is minus 14q squared. And minus 2 times positive 2 is minus 4. And notice your middle two terms are going to cancel out. 14q squared minus 14q squared, that's just 0. And so you do get back 49q to the fourth minus 4, which is what we started with. So in that sense, we can feel confident that this is the correct factorization here. So let's look at one more of these problems. And we're again going to be factoring a polynomial. So let's paste in our two formulas so that we can compare it and see if we either have this perfect square or a difference of squares, since we're trying to use structure to see if we can factor this polynomial. And since we have three different terms, we know we're not going to be using the difference of squares, because that, first of all, needs subtraction, and we don't have that here. But second of all, a difference of squares is always one term minus another term where both of those terms are squared. So likely for these problems, this is going to be a perfect square. But let's rewrite this first and then think about it. So we have this 9m squared plus 30 times mn plus 25n squared. Now, if you encountered this problem without being prompted that it's going to be one of these, then it's a little bit difficult to tell that this is a perfect square and we can use this formula. But one piece of advice is to ask yourself, can any of these terms be rewritten as something squared? So 9m squared, notice we can rewrite that as 3m to the second power. Since if we remultiply this out, that's 3m times 3m, which is 9m squared. And likewise, this 25n squared can be rewritten as 5n to the second power. Since again, if you multiply 5n by 5n, you do get back 25n squared. And so rewriting these first and last terms as something squared gives us a hint that this is possibly a perfect square. So at this point, we just need to determine, can we rewrite this middle one, this middle term here, as twice this first term multiplied by the last term, ignoring the squares. And we know we can write it as twice 15mn. So let me first just start with that. And let's continue working down here. So we can rewrite the first term, that's 3m squared. And then we're looking for 3m times 5n for this middle part here. And 15 can be broken up into 3 times 5. And we can rearrange the m and the n to go with their respective parts. So we have plus 2 multiplied by, let's say, 3m. And what would be left if we factored out a 3m from 15 times mn would be a 5 and an n. So we would be left with 5n there. And lastly, we have this 5n squared. So this does match up with our formula. We have some number squared plus twice that number multiplied by another expression, which we can call y, plus that expression y squared. So we can match it up perfectly with our formula here. And because we can do that, we can rewrite this now in its factored form as x plus y squared, where we figured out that x is just 3m and y is 5n. So writing it in its factored form, we would have 3mx plus 5n, which is y. So 3m plus 5n, and we're going to square that. So this is what we think is our factored form. And to check this, we would just need to multiply this back out. So we would rewrite it twice and then use distribution to multiply it back out. But I will leave that as an exercise for you. So I encourage you, check your work here, try to multiply this back out and see if you do get back this original expression, this original polynomial that we were given.